The actual quantity goals embraced by an organization are affected by customer demands, which is the level of quality customers are willing to pay for. With that being said, I'll be talking about how the Six Sigma approach assists in quality control. So in statistics, the Greek letter sigma stands for standard deviation, which is the measure of dispersion of a set of observations around the mean. We can use a standard normal curve with a mean of 0 and standard deviation of 1 to represent probabilities. For example, the area to the right of +3 standard deviations, aka 3 sigma, is very small, approximately 1.4%. We use these probabilities to find the number of defects per million. At a 3 sigma performance level, there are approximately 14,000 defects per million. A 4 sigma performance level would translate to approximately 320 defects per million, while a 6 sigma performance level would translate to only 0.01 defects per million. In short, sigma can be used to set quality expectations. The higher the sigma level, the higher the quality expectation. The move from, say, a 3 sigma to a 6 sigma quality level is dramatic, as each sigma is a big jump in quality control. For this reason, 6 sigma is not likely the goal for all processes and operations. The appropriate quality expectation is a function of the strategic importance of the process and anticipated costs of taking the process to an increasingly higher level of quality. Besides using Six Sigma to set quality expectations, it can also be used as a management philosophy which drives companies into bettering products, services, and processes. The goal is to improve businesses by getting rid of defects and errors, reducing manufacturing cycle times and costs, enhancing productivity, meeting customer expectations, and improving return on investment in both manufacturing and service operations. An example of a result produced by using the Six Sigma approach is the reduction of defects and product variation in a textile finishing plant. Well, how exactly are these results produced, one might ask? This is through the simple problem-solving methodology called DMAIC, which stands for design, measure, analyze, improve, and control. Typically, the application of Six Sigma uses cross-functional teams, more or less on a consulting project basis. In the design stage of the project, the Six Sigma team defines the problem and specifies the deliverables of the project. In the measure stage, the team collects relevant process performance data. In the analyze stage, the team tries to uncover root causes of an underlying quality problem. This is followed by the improve stage, where proposed solutions to the underlying problem are generated and then implemented. Finally, in the control stage of the project, appropriate controls are put in place to ensure that the identified problem does not reoccur. To better understand the define stage, tools are used to help find the problem. One example of these tools is a control chart. A control chart plots successive observations of a quality characteristic to help determine whether a process is in control. The typical control chart has a horizontal axis representing units, time intervals, batch numbers, or production runs, and has a vertical axis indicating a performance measure. The vertical measure has a specified range of variations, which are referred to as upper and lower limits, based on the mean and standard deviation of the observed quality characteristic. Points outside the limits may signal quality failures or an out-of-control process. Points must also be random within the limits, which means they should show no apparent patterns or runs, with an approximately equal number of points above and below the centerline. Looking at workstation C in the example, even though all points are within the limits, the control chart reveals that the points are drifting upward, which is a run. Management may want to launch an investigation because the trend suggests that in the near future, the operation may produce drill bits outside the control limits. So after major quality problems have been identified, cause and effect diagrams may be used in the analyze stage. A cause and effect diagram, also known as a fishbone diagram, organizes a chain of causes and effects to sort out root causes of an identified quality problem. The diagram consists of a spine, ribs, and bones. At the right end of the horizontal spine is an identified quality problem. Each rib pointing into the spine describes the main cause of the problem. Bones pointing to each rib are contributing factors to the cause. So the four main causes for quality manufacturing problems include machines, materials, methods, and manpower. If we take a look at an example for chocolate mousse quality problem, we see there's a 20% rejection rate. The four causes are the ones I just mentioned, with each cause having two related contributing factors. As you can see, the reason that the machine added to the problem was that the equipment was not calibrated correctly and the timer functioned erratically. I hope you learned why Six Sigma assists in quality control. It can be used to set quality expectations or be used as a management philosophy. Tools are used to help in the dynamic process, and management works to make sure the approach is successful. Thank you.